Good evening, sir. Can you please unmute yourself, and if possible, can you switch on your video? Thank you, thank you. Satish ji, can you please, if possible, can you?
Yeah, I'm here. I'm audible?
Yeah. Audible.
Really sorry for inconvenience, and maybe, it's a technical word, so digital word, many of time we are, getting this type of issue, but hope next all thing will be fine. Okay. Satish ji, are you able to see my screen?
Yes, I can able to see sir screen.
Okay.
Sir screen, yeah.
Okay, and okay, I'm also making you a co-host. So co-host, okay, so, and can you unmute yourself, Satish ji, please? Oh.
Yes,
okay.
I am muted.
Okay, thank you. So, without wasting time, please proceed. Dr. Satish, to all participants, sorry for inconvenience, and welcome you all on the 5th lecture on this radiation safety web lecture series, and it will be presented by Dr. G Sahni, sir. So I will request to Dr. Satish, please proceed, do the moderation and proceed for this lecture.
Yeah. Good afternoon to everyone. It's a great pleasure to invite Dr. G Sahni sir for regarding this CMPI webinar on shielding calculation for radiotherapy facilities. A short introduction about sir. Sir is designation head medical applications section, MAS and Atomic Energy Regulatory Board. He has a total experience of about more than 20 years in having radiotherapy, nuclear medicine, radiology, and also research facilities across the country. And he is also involved in R&D in shielding dosimetry and QA protocols. He has a safety review for licensing of first proton therapy facility. And he has an area of interest on regulation of medical radiation facility, radiation protection, radiation shielding, dosimetry, and also in QA. He is also involved in regulation of hadron therapy facility, and also in developing regulation for radiation facility, and also in R&D in shielding, dosimetry, and QA protocols. And his major achievements and his educational things started with MSc Physics, and also he has done PhD in Physics, and he has completed OCS and has completed DFP. And his adjunct faculty, Mahi Manipal, and he has awarded Airbus Outstanding Performance for his remarkable contribution in regulation of radiotherapy facilities across the country and research and development activities in the field of radiation safety and medical physics. And he also awarded Airbus Group Achievement Award on strengthening regulatory control, radiation safety, and simplification for regulatory process in diagnostic radiology practice. And he also won the IMP's Best Paper Award for his paper for his research work. And he has a publication of more than 57 papers, which includes original articles published in peer-reviewed national and international journals and other books and abstracts. Now it's the time I'm handing over to Dr. Sahni sir for a presentation.
Thank you, Dr. Satish. Thanks for introduction and nice words. And I would like to be very, very thankful to CMPI of BRL and in particular Dr. Bhatt for organizing such a wonderful series of lectures, which is benefited not for professional but also the students. So without wasting time, let us start because already there is some technical hitch and we face some problem. So let us start now. So my topic would be the shielding calculation for radiotherapy facility. And if you look at the number of radiotherapy facilities, there are numerous in numbers.
Can
Like, it sounds
be done.
I'm audible?
Just a call.
Okay. Dr. Bhatt, I'm audible?
So you are audible, and I will request to all participants, please turn off your mic and turn off your video for smooth functioning of this web lecture. Thank you.
Yes. So look at this table. What we have right now, we have external beam therapy and radiotherapy. External beam therapy, we have medical accelerator, then we have tomotherapy, halcyon, cyber knife, gamma knife, telecobalt, and hadron therapy facility, which is based on either proton or carbon. And if you look at that energy, we have 4 to 18 MB. Now days multiple up to 5 to 7 photon beam energies also are coming, depending on the user's choice, and the manufacturer able to make this one. And now electron beam also can go 4 to 25 MB and dose rate. So dose rate is also for triple F beam can go up to 2.4 gray per minute, and because of the removal of flattening filter and so on. Then in brachytherapy, we have cobalt 60 or iridium based, both are in the country and so in the worldwide. And IORT based, we have around 40 to 50 kV soft accelerators being produced, which is used for the treatment of tumor after surgery. And so many ocular brachytherapy also there. And of course, cesium 137 manual brachytherapy is almost diminished from the practice. So, yeah. So now the question is, why the shielding requirement? So what is the purpose of shielding? Or the purpose of radiation shielding is to arrive adequate radiation shielding thickness of the wall, ceiling, or the radiation insulation, so that radiation dosage to the radiation workers, members of general public, shall not exceed their dose limits. Next, please. So, but that national or international recommendation on the shielding calculation methods, which are widely used across the globe, very popular is NCRP report, National Commission on Radiation Protection, that is US based. So for radiotherapy is report number 151, structural shielding design and evaluation of mega voltage X-ray and gamma radiotherapy shielding facilities. It was published in 2005, and after 1 year, IAEA has also published similar type of report, the radiation protection in design of radiotherapy facility. And there is a beautiful book written by McGilly. Third edition also has come this in 2020, radiation shielding technique for radiation oncology facility. It's very thin book, but it gives all the facilities. So I happen to be reviewer of this book, and then Institute of Physics and Engineering Medicine, so report number 75. There is also this glimpse of design and shielding of radiotherapy treatment facilities. It was published in 2017. And one more popular NCRP report 79, especially for high energy accelerator, where neutron contamination from medical linear accelerator is there. So that consideration, if you want to do that, you can refer this one. Next, please. So now, what is the shielding calculation techniques for the medical radiation facilities? It can be analytical technique, or it can be computational techniques. This is Monte Carlo simulation. So MCNP, sorry, Monte Carlo N particle. This is another type of code, and then we have Monte Carlo based another code. We have Fluka, there's Genfold, Enlope, EGS, Beam, NRC. So many codes are there. One can refer. So only what most popularly used shielding calculation are analytical technique, because that analytical techniques are easy to follow. Whereas the Monte Carlo, it takes larger time, and especially, but it is very useful in case of hadron therapy facility, because really the analytical technique is not alone cannot do the job. So Monte Carlo is very, very useful there. And then let us talk about some terminology. Next, please. Again, next. So you have a controlled area, another is uncontrolled area. Controlled area, which is limited, which has limited access, in which the occupational exposure to the person is under supervision. For example, control, even treatment room, nobody can do. Uncontrolled area, so these are like offices, examination room, arrest room. These are uncontrolled. You don't have any control. People can occupy, they can come and occupy. So next, please. So consider this kind of location. So we can have a shielding design goals. So shielding design goal, what is shielding design goal? Whatever those limits or those constraints you are choosing. So putting the shielding, after putting shielding, those whatever you have chosen should not exceed. So it's for members of sorry, for members of public, it is 1 millisievert per annum. So you can derive, you can divide it by 50 weeks, then you will arrive around 20 mR per week or 2 mR per week or 20 microsievert per week for publics. Similarly, for radiation worker, you could derive from 20 millisievert per year. Then you divide by 50 weeks, you can get 40 mR per week or 400 microsievert per week. These are the design goals. So based on the type of equivalency, you have to consider the design goal limits. And then ARB has also issued a safety directive in 91, just after publication of ICRP 60. So earlier dose limit was higher, and there they have reduced to 20 millisievert average dose per year for the worker and 1 millisievert for the public. So this was again notified in 91, and shielding calculation is being done by using this design goal based on the workers or public. Next, please. Then, what are the protective barriers? The protective barriers either can be primary or can be secondary. So, primary barrier with so whole wall is not the primary barrier. A portion of wall or ceiling which faces the direct radiation, collimated radiation, called primary radiation, and other than that, all are called secondary barrier. So, next, please. So look at this one. At the primary barrier, we are going to receive direct radiation at the patient is lying, and the secondary barrier at the wall perpendicular depicted there. You can see that which receives the leakage radiation from the unit head and scattered radiation from the patient and the wall. So these are the radiation coming. So now next, please. So now, what are the optimizing parameters we use for shielding? For example, if it is cesium-137 manual brachytherapy, so you can say that radiation is continuously on for 24 hours and up to 5 weeks in a day, 5 days in a week. So, but here in case of accelerator, telegamma, brachytherapy, remote touchdown brachytherapy, here all we are using very less beam on time. The rest of the beam is off. So during the beam off, there is no radiation. The shielding can be reduced accordingly. So that's what concept of workload has come into picture. So workload, how we are deriving that? We can say that a dose per patient, how much it is prescribed per fraction, and then how many patients you can treat per day, and then 5 days per week is the treatment regime. So this will be multiplied by the, and then a dose at Dmax will increase by the if you divide by PDD value, because a tumor dose, tumor death dose will be reduced by factor of PDD. So if you divide by PDT, you get the dose at Dmax. So that so we define dose workload as workload is the integral of dose at 1 meter from treating all the patient per week. So its unit centigrade or gray per week at a distance of 1 meter. Sorry. Okay. So for example, for 15 MB, you can calculate for 15 MB, you have to divide into because all the accelerators are coming with dual energy. People are taking 6 and 15 or 6 and 18. So accordingly, you can divide the number of patients that can be treated with high energy. So with high energy, normally it is not being treated more than 50%. So the worst case scenario is taken around 35 patients per day can be treated with high energy. The rest will be treated with 6 ml. And then if you 200 centigrade per week, centigrade per patient, and then again divide by PDT, and then 5 days per week, you get the workload around 0.5, 10⁵ centigrade per week at 1 meter. And for 6 MB alone, if you calculate, and then you calculate 200 centigrade per patient and 70 patients per day, 5 days per week, and divided by PDT value, we'll get around 10⁵ centigrade per week at a distance of 1 meter. Next, please. So similarly for telecobalt also you can derive, because here 400 centigrade per patient, it is after division of PDT value. For example, if you give 200 centigrade per patient, and if you take depth of tumor is 10 centimeter, mid of the patient plane, then around 56% PDT precisely, but for shielding purpose, I have taken 50%. Then become 4 centigrade per patient, 70 patients per day, 5 days per week, and you get around 1.5 to 10⁵ centigrade per week at a distance of 1 meter. And then similarly for CyberKnife, tomotherapy, all the workload you can calculate. So for CyberKnife, again I'll explain in detail later slide. Just for workload, you can have this one. CyberKnife has, because it is something different than conventional accelerator. Here, beam on time is very high in tomotherapy, CyberKnife, Halcyon. So that's what even for primary, you need to consider for head leakage. So primary plus head leakage radiation is both considered even for primary beam. So you can determine, like NCR 51, what they have assumed that around 12.5 gray per patient and 16 patients per day and 5 days per week. These are the maximum number of patients that could be treated in a week. And because in CyberKnife, there's ISO center, basically pseudo ISO center. So it can vary from, I think, 60 to 120 centimeter, and 80 centimeter is taken for output measurement or shielding calculation. So if you translate to 1 meter, then just multiply by university square law, you get around 6.4 10⁵ centigrade per week at 1 meter. And for leakage workload, just multiply by IMRT factor into primary workload, you'll get around 9.6 10⁵ centigrade per week. And come to the workload for tomotherapy. Similar way for tomotherapy also, there is the primary workload and leakage workload. So leakage workload, again, you can determine by maximum 32 patients can be treated per day, and 7-minute average beam on time per patient. 5 days per week. And again, SAD is 85 centimeter. Then at 1 meter, just multiply by inverse square law and multiply by dose rate. You'll get around 7 into 10 to the power 5 centigrade per week at 1 meter. And then IMRT factor for tomotherapy comes around 16. Just then the relation between primary and leakage workload is leakage workload is equal to IMRT factor into primary workload factor. So if here because leakage workload we have, then divide by workload IMRT factor, then we get primary workload 5 into 10 to the power 4 centigrade per week at a distance of 1 meter. Next, please. Okay. So use factor is also another very important parameter, and is a fraction of basically primary beam workload that is directed towards a given barrier. So the value of use factor depend on the type of installation protective barrier. For example, if you go for medical accelerator or telecovert, then one is for gantry pointing down, because down always most of the dosimetry you do it always, suppose there is something below the basement, then you have to have 1. Otherwise, for all coordinate angle, you have to take use factor 1/4. And leakage and scatter is always 1 because secondary barrier will always receive the leakage and scatter whenever machine is on. So in factor you have to take 1. Sorry. And the use factors for tomotherapy in Halcyon is around 0.1. So you can save the thickness around 1 TVT if you look at that. And come to use factor for cyber knife is very, very less, even lesser than tomotherapy Halcyon. It comes around 0.05. I'll explain in detail in later slide. Here, just I'm giving the glimpse. And a use factor for secondary barrier radiotherapy is always 1. So next, please. So look at that based on the calculation. If you look at that estimated workload, use factor, and various facilities, what do you have for accelerator, high energy, low energy, tomotherapy, cyber knife, Halcyon, telecovert. Thicknesses would be different because of all the workload due to leakage, workload due to primary, and use factor, all are different for different machine, and hence these will be resulting different thickness. Otherwise, though physics wise thickness should be same, because I am giving TVT will be same, and energy is same, material is same, then design goal is same, then it should come same, but doesn't come because of this parameter. Next, please. Next, optimizing parameter is occupancy factor. Occupancy factor nothing but the fraction of beam on time that the exposed individual is present while beam is on. For example, your machine is on for 2 minutes during all 4 fractions, and that person is occupying for only 2 hours. So use factor, occupancy factor become 2/8, so 1/4. So if always present, then full occupancy 1. Otherwise, you can keep on reducing, and it can save the thickness. For example, if you take partial occupancy 1/4 T, so 2 HVD thickness can be saved. So accordingly, these are the optimizing parameters. So next, please. So what is the information? What are the information required for shielding design of installation with respect to machine specification? So look at this machine. In the blue color, what is written is the gantry stand. So this is fixed on the floor, and there will be axle on the gantry. So a gantry will be rotating on its axis. So red color shown, whatever the arrow is the axis of rotation. Always shouldn't get confused. So this axis of rotation will be just passing through axis through which it is rotating. So that is very important parameter. And from target to this axis of rotation, distance would be called SAD. क्या अरे तो मैं लेक्चर ले रहा हूँ बाद में करूँ yes. So this axis of rotation, you can see that it is varying. For example, tomotherapy, target to axis of rotation is 85 centimeter. For example, telecobalt, target to or source to axis of rotation is 80 centimeter. And halcyon is 1 meter, accelerator is 1 meter. So these all are varying. And there will be couch axis, and there will be collimator axis, all wherever meeting. So they this is called isocenter, because this isocenter is wandering in a sphere of some mm diameter. For example, accelerator, it is wandering, it should be within 1 mm radius or 2 mm dia. In cobalt, it can go to 2 mm dia or 4 mm, sorry, 2 mm radius or 4 mm dia, because their head is heavier than linear because of shielding to be provided in off condition also. So the parameter is required is where site location, accessibility, image guard, door interlock, and equipment type is required, energy, dose rate, field size, a special technique like MRT and other things. And so many parameters need to be checked and taken into consideration. Occupancy, dose limit, etc. So next, please. So what are the assumptions are being taken worldwide for shielding calculation? Is a attenuation of primary beam by patient is neglected. We don't while calculating the shielding, we see that there is no patient, but actually there is a patient. Then barrier thickness often assume perpendicular incidence of radiation, but other than there will be a lot of obliquity, and means slant thickness will be passing, and hence thickness will be more, so radiation level will be less. So again, there is a conservation. So because of these all parameters, there will be always radiation level less than what is calculated, conservatively safer. So our planning should be done based on calculation. It should be conservatively safe. That is our objective. So next, please. So what are the shielding material commonly being used for making bunker? So best way to use ordinary concrete, and then heavy concrete is also being used. What is heavy concrete? Just like depleted uranium is defined. Uranium is less if concentration is 235 depletes. That case we say depleted uranium. Similarly, heavy concrete, if density of concrete material exceeds 2.35 gram per cc, then it's called heavy concrete. So not be at 3 to 5 gram per cc, it is a density of high density concrete can be achieved commercially. And we have lead, steel, earth. So heavy concrete and steel, lead, these are useful in saving the space where you are retrofitting, you are changing from low energy to high energy. But sorry, high energy, again, that is a problem because there will be production of neutron in the material itself. So heavy density concrete and lead, steel are not being used alone. However, it can be sandwiched between the ordinary concrete, that can be used. And but in case of obtuse energy 10 MB, easily can be used even this high density concrete, can save the space. Like for example, telecobalt machine, you are decommissioning, you are going to put tomotherapy or halcyon. So using this high jet material within the space, you can fit your halcyon atomotherapy machine in such bunkers. And earth is also another important study material where if user is planning to set up in the basement, so earth occupied within its boundary can be used as a shielding material. So here also we can save a lot of money for shielding construction of the wall. Please next. So just you have a top view. If you look, especially for students, this is very clear. If you just like we say, top eye view. So if you sit at the ceiling, without ceiling, just to see that you can see bunker will look like. You can have left side primary, then right side also primary, then after that secondary, maze wall, and then there will be control also. So next. So based on the assumption, there was a calculation was done, and this typical standard was made, and it is available at our website. You can say that for dual energy, high energy accelerator 615, thickness can go at 220 centimeter into primary, because this, how we are going to decide this room dimension is given by the vendors. What is the dimension is required to install their machine and do the service, because not only operation but service and maintenance is also some space required. Then only vendor can say that what is the space is required. So normally 6x7 inner dimension they recommend that they require. So after that you have to put the thickness and go to next. So this is the another handmade drawing to understand how the ceiling will look like. First figure is floor plan. So if you cut from plane xx, then you can say right side cross section xs. You can say that ceiling thickness will be in the primary region, then uniform thickness, and left will be thickness of the primary barrier, primary wall, and right is wall B. And similarly, if you cut another plane y perpendicular to this central beam axis, then you can have a thickness just like right side third picture. You see that there is a protrusion and central beam axis is shown, and divergence is also seen. So you can have a better understanding. And then left side you have a maze with maze area, and first wall is maze wall, and thereafter wall between the control console and maze area. And ZZ cross section is the cross section passing through the maze area. So the portion of the ceiling which is exposed directly to radiation, thickness is higher, and thereafter can be reduced because of reduction of radiation by the maze wall. Next, please. So for shielding calculation, what we have to do? You need to consider the radiation components. What are the components? We say primary, leakage, patient scatter. So accordingly, we design the walls. So primary barrier, secondary barrier, and estimation of total radiation dose at entrance door. So these are the three types of radiation is to be evaluated for arriving the primary barrier, secondary barrier, and we have to estimate what is the radiation dose reaching at door entrance from all the components. Yes. Next, please. Yeah. So come to the how to calculate the primary barrier thicknesses. So reduction factor, we know that dose without shielding divided by dose with shielding. So dose with shielding at 1 meter will be WUT, you can say W because nothing is centigrade per week at 1 meter multiplied by use factor in that direction, and occupancy what is type of accuracy multiplied. So if this is the effective dose at 1 meter. If divided by d square, we say that distance dose will be at distance d without c, and whole divided by permissible dose limit p. So this will be reduction factor, and then take log of that reduction factor. We'll get the number of TBL. So thickness of primary barrier will be number of TBL. So arrive multiplied by 10th value layer of the material for that energy. Next, please. So this is for primary. Then once you have arrived the thickness, what should be the dimension, width of the primary barrier? So that depends on the what is the maximum field size available with that machine. For example, telecobalt 35 by 35, and for linear accelerator 40 by 40, and for LCON 28 by 20, and for tomotherapy 5 by 40 centimeter. 5 is the only width which is going to be projected on the primary wall. So based on this, you can by simple trigonometrical geometry you can calculate width of primary barrier. You can see right picture, and left you can see that how the beam is diverging, and the more the distance at the distance of thin wall is placed, then divergence is more. So according beam width has to be more. So right side, look at the equation is derived. Barrier width will be source to axis distance plus distance of wall from isocenter, plus if there is a protrusion, you add protrusion, multiply by one dimension of the field width divided by SAT. So this will be width of the barrier, but radiation is not going to stop just like other things. So it has, once it fall on a barrier, it will have reflecting, so there will be scattering. So scattering around 12 degrees is predominant. So corresponding to that scattering angle, it comes around 30 centimeter margin to give of this material, concretes. So it will be taken care. So if you add from both sides, you have to give, so 30 into 2, 30 plus 30. So 60 centimeter you have to add it. So you can see you can achieve the width of the primary barrier. Next, please. So you have 3 scenarios in calculating the primary barrier width. So one is what is the maximum field size? You can go 40 by 40, and because if you rotate collimator by 45 angle maximum, then you get the length of beam diverging on the primary barrier equal to diagonal axis. So diagonal, you can say 14 to root 2. That is very simple. So there should be maximum projection on the primary bed, and then 30 into 2, 60 centimeter that can be added. That will be primary barrier width. But in practice, all our clinical physics, you might be seeing that around most of the cases can be done within 20 by 20 field size. So it is again in practice, we don't use multiply by root 2. We take only whatever the field dimension projection at isocenter plus this DC is what is that distance, because SAT is 1 meter, so numerator is not there. So denominator is 1. So DC is only a distance from the target to end of the producer. So accordingly, for example, in first case, target to protrusion distance, protrusion outside. So you have to take distance from target to just ending the protrusion. In the second picture, most commonly we use in our India, protrusion is inside the bunker. So you can take distance from target to the end of the protrusion, means just where the secondary barrier starts. So it is second scenario. Third scenario, if you are using metallic thing like steel or lead and sandwiching between, and then you have to take distance from target to a distal end of the metallic plate. Then you calculate the width. Next, please. Now, for example, just have a feel. If it is that primary, find out the shielding thickness and width of primary barrier to be made of concrete for 6 MB linear accelerator, and beyond the barrier location is to be occupied by a receptionist. So who is a receptionist? Receptionist is the non-radiation worker, members of public. And here in this is, if distance between the ISO center and the point of interest is taken 7 meters. So the distance from target will be 1 plus SAD plus distance from ISO center to point of interest 7. So 1 plus 7. And then workload for 6 MB, just we have calculated before that 10 per 5 centigrade per week at 1 meter. And each factor for primary will be 1/4, nothing but 0.25. And then the occupancy factor 1 divided by permissible dose limit for members of public is 2 MR. So 2 MR you can say 2 into 10 to the minus 3 centigrade per week, so that unit get cancelled, get converted, and divided by 1 plus 7, that means D square. And this will be number of TBT multiplied by 34 TBL value. You get the thickness around 180 centimeter of concrete. And then width, they're using previous equation. You can, before slide, this slide had shown that SAD plus distance from ISO center to point of interest, D, and multiply by field dimension divided by SAD. So SAD is 1 meter, and then D is 7 meter, multiply 40 divided 1 meter. And meter get cancelled, then you can use field dimension, centimeter also, no problem. So it comes around 380 centimeters, the total width of primary barrier with margin. This next. So now come to the secondary barrier. How to calculate secondary barrier thickness. So secondary barrier, as already explained, which receive the radiation due to head leakage, due to patient scatter and wall scatter. This all three component radiation will be present whenever you are switching on the beam. Next, please. So, but only wall scatter radiation will be negligible. So that is neglected from the calculation. Only patient head leakage and patient scatter radiation are dominant or secondary value. So due to head leakage, you can say the reduction factor is alpha 0 W2 by TBS square. What is alpha? Alpha 0, nothing but head leakage. What is the head leakage? Now we use 0.1% or 0.001 into workload use factor divided by permissible dose limit divided by ds. ds, this distance is taken from the ISO center to point of interest, not the source, because source is rotating in the vertical plane and it is not fixed. So source is taken at the ISO center, an average location. And moreover, this will be more safer because distance will be shorter compared to if you, there will be when you're rotating the accelerator around a patient in vertical plane, and then distance from the point of interest beyond the wall to the source will be higher than the distance of point of interest from the ISO center. So it is for considerably safer, it is taken from ISO center. So again, and then you can calculate thickness due to head leakage is nothing but number of TBL. You can calculate taking log of RF multiply TBL value. Next, please. Now there will be patient scatter. So thickness reduction factor due to patient scatter, similar way you can calculate. A is the patient scatter fraction, Means it is a tabulated value, function of energy, function of material, function of angle. So once patient lying on the table, you open 20 by 20 feet size. So every room angle, you measure what is the radiation level at 1 meter along each angle. Then accordingly, whatever as per your requirement, while calculating secondary value, you can choose that value of A, and then workload, use factor, and occupancy factor. And this F by 400, nothing but F is a field dimension maximum. For example, accelerator, take F nothing but 40 by 40 centimeter square. And this A value is determined by opening collimator 20 by 20 field size. So that's why 20 by 20 into 20 becomes 400. F by 400 is a factor used in a numerator, and then come to denominator divided by permissible dose limit, and distance DSC is the distance from target to the scattering location from the patient, and D is the distance from moisture center to point of interest. Just you calculate, you get RF, then take log of base 10, you get the number of TVL, and then multiply with TVL value, you get the thickness due to patient scatter. So now, in this case, we get two thicknesses. What should be my final thickness? So final thickness, there is a methods for determining final thickness. For case 1, if you just take the difference between this thickness due to leakage obtained, thickness due to patient scatter, what you have obtained from the previous slide, and if difference is greater than 1 TVL, then final thickness becomes the maximum of these two thicknesses. Means thickness due to leakage, thickness due to patient is take up maximum of them. If the difference between thickness due to leakage and patient scatter is less than 1 TVL, then you have to add 1 HBT to the maximum of leakage and patient scatter. Next, please. Just for understanding, I have given one example. Next, please, slide. So, for example, find out final thickness of a secondary barrier if thickness due to head leakage and patient scatter workload are required to be 105 centimeter and 90 centimeter respectively. And then you can assume TVL of concrete is 34 centimeter for head leakage of 6 MB length. So then you take the difference, TL minus TPS equals to 105 minus 90 centimeter becomes 15 centimeter, and which is less than 34 centimeter of that, means 1 TVL, less than 1 TVL. Then you have to add 1 HBT, maximum of this. What is the maximum value among 105 and 90? It's 105. So 105 plus add 1 HBT. There's a TVT you can divide by 3.3 becomes the HBT. So it is around 115.3 centimeters. So this, I think, gives a clear-cut idea. Please next. So similarly, you can calculate the thickness of roof and floor as well. So only the calculating thickness for floor, if there is a basement, you have to take use factor 1, only 1. Next, please. Now, third, now your primary barrier is over, secondary barrier is over. Come to the what should be the door thickness. So door thickness, if you do not have a mesh wall, then you have to have what we say motorized door to be shielded at the entrance door because of direct radiation is coming. So in order to avoid this, you need to provide mesh wall thickness, So what we have, what are the components are reaching at the entrance door? Would we look at the 4 components? One is the radiation directly reaching head leakage transmitted through the maze DT, and then head leakage, which is scattered from the surface, room surface, and then reaching to the entrance door, that is called DL. And then whatever radiation is falling on the patient, then thereafter it is getting scattered, and that scattered radiation again it is reflected back from the walls and surfaces to the entrance door, that is DP. And then some radiation transmitted through the patient and hitting on the primary barrier, and then deflecting to the entrance door, that is also known as DW. So at all components, this is due to photon. If there is a 15 MB, more than 10 MB also, then you have to add a neutron dose as well. So next, please. So now, one by one component, I explained that dose arising from the patient scatter, you can determine dP is equal to AWUT by into F by 100 into this radiation falling on the maze area, so which is to be reflected by area AM in the direction to the entrance door, and small am is nothing but reflection coefficient. Reflection coefficient nothing but in that particular it is a function of incident angle and reflection angle and material. So suppose at 45 degree it is coming incident and reflecting at 0 degree means along the normal. So you can say this value is available in table, can use for this scenario, and divided by DSCA, means distance from target to scattering patient surface, you can say. D1 is the distance from isocenter to first reflection surface, and D2 is the distance from reflection point to entrance door. In this way, you can calculate a dose reaching at entrance door due to patient scatter. Next, please. Then second component is dose arising from primary beam scattered by wall, means transmitting through patient, and that radiation is hitting, striking the primary wall. From there, it is reflecting. So you can calculate a dose due to wall scattering is use workload and use factor multiplied by distance from target to area of reflection is to the wall. And then again, these are the alpha is nothing but albedo factor into area. AS, capital AS means area of reflection, whatever projected field size. So you can use divided by distance from this center of the beam to center of the maze, that is called dr square. And then similarly another reflection, similar way another factor will be there. So you can calculate this dose. Second component. The third component is the dose arising from the head leakage scattered to the maze entrance door. So alpha 0 is on position leakage, means 0.1% WUT into this will be dose at 1 meter, and this distance D1 divided D1 square. So this dose will be coming at near scattering area, whereas AM is capital AM is nothing but area of scatter. A small AM is nothing but albedo factor, means reflection coefficient. It is value is available in table. D2 is the distance from this area of reflection and entrance door. Then similarly, you can calculate the dose due to head leakage radiation scattered back to the entrance door. Next, please. And then fourth component, dose arising from the head leakage transmission through maze at entrance door. So just you say that alpha is nothing but on position leakage and WUT divided by dt square. dt nothing but distance from target to point of interest, and this is the without shield, because you have shielding of thickness. T is a slant thickness. So slant thickness is always higher than thickness of the mace. So divided by 10 raised power T by TVL are, if you take in numerator, so 10 raised power minus T upon TVL. Okay. I'm audible? Yes. Yeah. Dr. Bhatt, I'm audible?
Yes, sir. Yes, sir. Please, please go ahead, sir.
Okay. Okay. So this fourth component, I think it's clear. So next, go to next slide. So what we do is basically in all condition we have taken use factor 1/4. Then if you add it all the radiation, it should be multiplied by 4 because there is a 4-band triangle. But it is it was overestimated. So I think McGillney et al. They said that no, it should not be multiplied by 4. It should be multiplied by a factor of 2.64. And all you add all components, this will be a dose, total dose due to all components reaching at interest dose. Okay. So what is the importance of this dose? Suppose you want to know the thickness of the what we say maze. What is the thickness of the maze? In cobalt, you might have seen 85 centimeters, something like that. And I think halcyon, it is around 80 centimeters, something like that. I'm not remembering. So that is thickness comes. How it comes, thickness? How much thickness? So thickness has to be decided because at control console there is a allowed dose limit is 40 mR per week because there is radiation work. So 40 mR is due to all radiation, all 4 components and radiation coming through the. What is done is remove third component transmitted dose to the maze wall. You calculate all 3 components, dP, dW, dL, and sum them off all 3 and subtract from 40 mR. That will be the dose available, permissible dose available for calculation of thickness of maze. So accordingly, that can be calculated. So we just I'll touch upon neutron radiation also. Though it's very complex, we take 10 to 15 lectures, then it covers all. Otherwise, a really difficult time within 1 hour to complete. So just I'll give the idea. So neutron from high energy accelerator, when the energy of photon exceeding 10 MeV, there will be production of neutron. And if more and more energy, there is a huge production of neutron. So that's what more than 18 MeV X-ray are not being used for treatment. Otherwise, for thicker patient, you can go for high energy, but there would be neutron concentration is very high. So what we do that the neutron fluence is calculated due to direct neutron radiation, scattered neutron, thermal neutron, all 3, and capture gamma. So because whenever neutron, there will be gamma radiation. So both components of radiation to be evaluated, and then accordingly proper shielding arrangements to be managed. Next, please. So each type of component, how we are calculated. So we calculate the flux. Flux nothing but number of neutron per centimeter square. This is the fluence. So if you calculate the fluence, for example, Q1 nothing but the neutron source strength. That is number of neutrons emitted from the shielded accelerator head per unit photon dose at isocenter. Means if you give 1 gray dose at ICO center, what will be the number of production of neutrons from the accelerator? So this data is available for each type of machine, and the report or vendor will be provided. So divided by 4 by d square. D is nothing but distance where you are measuring the fluence. So divided by 4 by d square, you get the fluence due to direct neutron. Next, please. And now these neutrons are also scattering. So scattered neutrons from the room, you can calculate the fluence due to scattered radiation 5.4, and then Q nothing but yield of neutron and per gray dose divided by surface. Yes, what is yes? The surface area is the sum of all the wall area visible from the isocenter. You have to sum it and divide it. And then next, before that, you have gone. Okay, this one. So there will be thermoneutron. So thermoneutron also flux you can evaluate by this equation 1.26 Q1 divided by S. So total flux, you sum it all three fluxes of neutron, add it, you'll get the total flux. Next, please. Okay. So capture gamma and neutron dose and maze intras. The scattered neutron and capture gamma photon generated by neutrons with interest dose and maze intras must be estimated, because these neutrons are directly coming and maybe not 100%, maybe a few percentage. So they will be giving directly dose to the person who is going to occupy at the entrance door. And those neutrons which were interacted with the medium, say wall material, so they will produce the capture gamma. This because of nuclear reaction, the thermoneutron interacts with the medium that produces the gamma, that is called capture gamma. So person sitting at entrance door may get dose due to direct neutron dose as well as capture gamma. So this has to be estimated. So this capture gamma, neutron plus all 4 component of photon radiation. So you have to sum it off all, and it shall not exceed 40 mR per B. Then we say my design is okay. Otherwise, you have to provide borated shielding or high-density polyethylene you put in the entrance door. So you have to estimate. But because of design, what is being made in India is that it doesn't require any shielding at the door. If you're providing the same, what we say, maze length and thickness of the maze and all things. So even ordinary door is good enough, because ordinary door is not shielding radiation, but only for preventing a person going to treatment, unauthorized access. Okay, next please. So this is what about neutron hit to the material? It produces a capture gamma. So the total neutron fluence phi A at inner maze point A is shown at the right side, may be estimated from the neutron source sense Q1 and the distance D1 from the average position of neutron source to inner maze point A and surface area. All these parameters are known. You can calculate the flux. So you calculate the flux by this equation, you get total flux. And then there will be conversion factor. Next, go to next, please. So total dose, capture gamma dose will be for d phi equal to k into phi a 10 raised power minus d2 TVD. So D5 is the capture gamma dose in gray per isocenter photon gray for maze length D2. And what is the TVD, 10th value distance? So like photon, if providing material, so it produces the means thickness required to reduce the radiation by factor of 10 is called TVT or TVL. In neutron, we say that the distance required to reduce neutron dose by factor of 10 is called 10th value distance. So around 3.9 meter for 15 MeV, it reduces the energy, neutron dose by factor of 10. And 4.59, around 5 meter, you can take into 25 MeV energy is there of X-ray photon. Then TVD value for neutron will be around 5 meter. And what is the K? K nothing but neutron capture gamma dose. This is conversion factor. Fluence to dose equivalent. For example, 6.9 10 to the power minus 16 sievert per unit neutron dose fluence. So one fluence, 1 unit fluence will give this much dose. So W is nothing but weekly workload in gray at 1 meter, gray per week at 1 meter. And for TVT, it's also around 22 centimeter ordinary concrete offer the 10th value layer of this one for neutron. Means 22 centimeter concrete will reduce the neutron dose by factor of 10. So that was the D5 is the dose per unit fluence. Means per unit fluence is per gray it was calculated. So to multiply by workload, what is the workload in terms of gray? So you'll get the total dose due to capture gamma. So this is one component it can be estimated. Next, please. So neutron, now this is capture gamma. Come to the neutron equivalent dose at maze intervals. Suppose this H1 is neutron dose equivalent at 1 meter from the X-ray source per unit of per gray of X-ray dose, and AR cross section as well as the cross section area in the meter at the maze given the distance in meter from the isocenter to inner maze point, and D2 is the distance from this from S1 point to entrance door. And using that equation written in yellow, you can calculate the what is will be equivalent dose at if someone is occupies at entrance door. Please next. So once you calculated that DD is nothing but dose due to photons from all the 4 components: scattered, head leakage scattered, wall scattered, patient scattered, and leakage due to head leakage transmitted through a maze. Plus Dn is the nothing but neutron dose equivalent, and the DC is nothing but dose due to capture gamma. So add it all 3 components, then you get the total dose. It should be less than 40 mR per week for radiation worker. If members of public occupy, sorry, then it becomes it should not be more than 2 mR per week. Okay. So because of this varying parameter, you can see that shielding thickness requirement was primary bar, secondary barrier, shielding. For example, low energy accelerator 6 MB. Primary barrier comes 190. Tomotherapy, look at same energy of photon, but same design goal. It comes around 130 centimeter primary. Why it is? Reason is they have a beam stopper around 3 TBT, and then Halcyon also 135. Then again there is a beam stopper. So this is the reason why the thickness requirement of primary barrier has reduced. And of course, use factor is different for different machines, which is also playing parameters. Please next. So this we can say that thickness of shielding protective barrier is a function of workload, use factor, occupancy factor, permissible dose limit, and distance from the target to the point of interest, and type of material, and its dose. These are all playing parameters, which is in, changing the thickness requirement. That's what thickness for low energy accelerator, cyberknife, tomotherapy, or Halcyon or 6 ME, but thickness are different. This next. So I'll just briefly touch upon a small little on 2 to 3 types of facilities so that you can have understanding. And I'll take up first example is shielding calculation for tomotherapy. So tomotherapy, it is also now number has gone very much high in our country. So shielding requirement of such type of installation, how to estimate? You need to estimate to have a technical know-how about this one, only you can calculate. So who will give? Only vendor can give. So as per technical specification, is accelerator is rotating around the patient, just like a CT. In CT, executive rotates, and accelerator, tomotherapy, 6 MB compact accelerator rotate on sleeping guarantee, and there will be beam stopper intercepting the beam so that radiation can be reduced, and which is resulting reduction in thickness of primary barrier. And there will be bore dia around I think probably 85 centimeter, but we need for shielding is what is the distance from target to iso center. So it is 85 centimeter. Next, please. So look at this one. This is 6 MB beam is rotating with the patient, and slice by slice dose is given. And that as a result, doses are very high per fraction. If you even for delivering 2 gray per fraction, suppose 10 centimeter length of tumor, then 1 centimeter thickness you take of slice. So 10 times you have to deliver same amount of base. So dose becomes 10 times more. So accordingly, shielding would be more. That's what when had shielding they provided more, and they have beam stopper. So primary, secondary both are reduced radiation. So resulting less requirement of shielding thickness of the walls. And then all we know that the manufacturer is Accuray now, and it can treat up to 135 centimeter length, and source to exit distance is 85 centimeter in beam stopper, which has around 3 TBL value, and then maximum feed size at isolation 5/40, and maximum dose it can go 862,000 depending on model to model. And then here also approach is same as we have discussed about linear accelerator. We have to calculate the workload, but only the difference is here because beam on time is very high. Then as a result, leakage radiation from the head is very dominant, and resulting that thickness, additional thickness requirement due to head leakage as well for the even for primary radiation beam. Otherwise, for telecobalt and accelerator, we don't consider leakage radiation. Only primary, once shielding is provided for primary, and that is adequate for leakage radiation also. And then some noise is coming. So just you already explained that how to evaluate the workload in my previous slides. So For leakage workload around comes 7 into 10⁵ centigrade, whereas for linear accelerator it was coming around for 6 MB. It was coming 1 into 10⁵, means 7 times higher workload here in case of chromotherapy. Then IMRT factor is 16 as available in the literature. So we can derive workload due to primary, just divided by 16, we get around 5 into 10⁵ centigrade per week at 1 meter. So once we establish the workload, then we need to know what we say use factor, because this is a continuous rotation of the X-ray tube around this patient. Hence, it need to be determined use factor. So by its basic principle, use factor nothing but the fraction of demand time during which a particular wall barrier is facing primary radiation. So in this figure, you can see that alpha is the angle through which the radiation barrier is receiving. Once rotated more than alpha, that radiation, other portion of the barrier will receive the primary radiation. So it's a very complex geometry. So we have calculated, even we have published in this journal. You can download from the GMP website. This paper is very detailed calculations given. You can refer. So based on this derivation, we have arrived the relation between the SAD, nothing but source to isocenter to target distance and distance from isocenter to point of interest, and that tan theta nothing but angle corresponding to maximum field size, and then it determine 2 tan into 1 upon 1 plus r by d into tan theta by 2 by 360. By using this, you can determine. So value comes around 0.09. So now you need to know, once you have determined workload, you have to determine what we say use factor. So what is the room dimension is required? Who will tell? The vendor can tell what dimension is required, as I already explained. So as per their recommendation, is minimum dimension is 7 meter length, 6 meter width, and 3 meter height. So accordingly, you can calculate the street plan it, because you do not know what is the thickness. Then you have to say that just put, and behind the wall venti they need around 2.7 meter probably clearance. Contrary to our telecobot or etc., where we put at mid of the associated mid of the room. Here it's asymmetrical. So here that reduction factor formula also will be modified, because WUT by PD square is, when there is no beam attenuated, because here you have beam attenuated, then you have to multiply by transmission factor, means what is the transmission offered by beam stopper. So beam stopper is offering around 10 raised to 1 minus T upon TVT. So for lead it is a 5.7 TVL value, and they have provided thickness around 12.7. So you have to calculate what is the transmission factor, TF, 5.9, 10 raised to 1 minus 3. So now once you have determined this, put in the same equation with modified equation, you get the thickness. So around 98 centimeter is the thickness due to primary. Come to the, just you do the iteration, because now you have to add 98 centimeter in the earlier distance. So to exit distance 85 centimeter, the 3 meter is the distance from isocenter to inner distance, and around 0.9 meter thickness of the wall, what you have arrived. So now become the D is 4.383, and then replace with that, reduced thickness will be reduced. Now thickness is reduced to 92 centimeter from 98. Now this is the Now other component, thickness for primary barrier due to leakage radiation. Primary is over, now come to leakage radiation. So leakage radiation you can calculate log of RF nothing but alpha L WL UTY divided PD square into PS. Similar equation. So putting this value, you will get that thickness of primary barrier due to this leakage radiation is 127. Look at due to primary you are getting only 92, and whereas due to head leakage you are getting 127 centimeter thickness required to take care of the leakage radiation component, because there was beam stop. So now because two component of radiation are predominant, then you have to apply two source formula. So two source formula nothing but take the difference between T and TP. What is the whether less than 1 TBL? Yes, it is 25 cm less than 1 TBL. Then you have to add 1 SBT in the maximum of these two values. So 117 plus 10.3 centimeter, which comes around 130. And then barrier width here, because of 40 centimeter is on the lateral side, and 5 centimeter in the longitudinal patient axis. And okay, then you 23 centimeter width of primary barrier comes, but there should be margin of 30 centimeter each side, so it comes around 85 centimeter width if I adding 60 centimeter. Next, please. So in this way you can calculate. Just I gave the glimpse how to go about. If more detailed one, you just download the paper. Shielding consider for tomotherapy from GMP, but we have published. You can have better idea. Now, shielding calculation for what we say cyber knife. This is another specialized radiotherapy equipment. Again, it is using 6 MB and flat beam, and this be robotic arm. It has 6 degrees of freedom, and this, as I said, that there is no fixed size to center, so it is varying from 60 to 120 centimeter. So it is fixed at 80 centimeter for the purpose of output measurement and specification of output and the shielding calculation. SAD is taken 80 centimeter. Field size varies from 5 mm to 60 mm, means 5 mm, 10 mm, something like that. So many collimeters are there. Right now we have one machine has come in Meerut, that is MLC based recently. They have installed, and field size can go up to around 10 by 11 centimeter. Okay, next please. So distance between the target to isocenter can be varying, as I already said, 60 to 120. Pseudo centimeter, 80 centimeter is defined. Okay, next please. So what are the assumptions to be considered for calculation? So again, average dose, James Roger and so many authors have, even in NCRP 151 also considered 12.5 gray, and one patient can be treated in half an hour. So 8 hours it can go 60 patients, and number of beamlets per session can go from 100 to 250, because there is a what we say nodes. So on each nodes you can for beam fire from at different directions, so that even bigger size of tumor you can treat with the cyber knife by this technology. And in general, 100 to 250 beamlets, beam directions are being used for treatment. So accordingly, the use factor will reduce. So it's based on clinical data analysis by James Roger. They have concluded that the use factor is 0.05. It's a minimum among all modalities so far we have. Like chemotherapy, you have around 0.09 is 0.1, you can say, LC1 also 0.1. So here 0.05. So what does it mean? That means if there is 100 beams, so one location will face only 5 beams. So all walls and floors receive primary radiation except ceiling, and those at entrance due to scattered radiation from the patient is negligible because field size is very small. And IMRT factor here also goes 15, just like a tomotherapy where they are 16. And so the height of pseudo-isolation center from the floor is 92 centimeter. So based on there's a restriction on the direction of beam which cannot direct the ceiling. So ceiling will be considered as a secondary barrier. Yeah, this is the difference in 7.9. Okay. Okay. This one.
You want this slide or other one, sir?
Yeah.
You're on this slide. No?
Okay. This one. No?
Yeah.
Okay. Let's go back. Let's go back. One slide. One more slide. So workload and each factor already. So we have primary workload. So primary workload nothing but 12.5 gray per patient, 16% per day, 5 days per patient. This is at 80 centimeter. Multiply inverse square factor, nothing but 80 by 100 square. You get 640 gray or 6.4 times 4 centigrade per week at 1 meter. And for leakage workload, multiply by IMRT factor, you get the value of 9,600 gray per week at 1 meter. Then each factor already explained. Yes, please go to next. And then based on this, look at this drawing floor plan. Based on the requirement, around 6.5 into 7 divided into 3.5 meter height is the dimension. So you draw a drawing, that calculate thickness and then do the iteration. So doing iteration, it comes around 165 centimeter thickness. You can put it the thickness. So what are the considerations? Just next, please. Next. So wall A left was the wall A identified. This is the primary, head leakage radiation, and patient miscarriage. Because patient will be negligible because of field size very small. However, so only you have to consider primary and head leakage radiation. Next, please. So let us calculate one by one. The thickness required due to primary radiation would be nothing but a reduction factor. Take that WE2 by PD square and put the value of W of primary and occupancy factor 1, use factor 0.05, permissible limit 2 MR per week, and distance will be target to isocenter is 0.8 meter, then from isocenter to point of interest is 3.25, and then first you do without 1.65, I think thickness we do not know. Then you calculate, then some thickness will come. Now you have to add the thickness, then you get different distance, higher distance. Then second iteration you get lesser thickness of the wall because the distance is more. And number of TVT nothing but take the log of RF multiply by TVT, then we give the thickness. TVL is less because of triple F beam and low field size. So you get around 154.8 centimeter of this one. Thickness of concrete due to primary radiation. Next, please. Now, what will be thickness required due to head leakage? Here, because D mountain is very high here also. That's what head leakage radiation also one of the contributing radiation which to be considered for primary radiation, because here all the walls and floor will be primary and ceiling will be secondary. And then you have a workload for leakage is 9,600 gray per week. Then same formula here. Alpha naught WL UT by PD square. Then putting the value, will get thickness due to leakage 140 1.9 centimeter. Next, please. So you got the two value. Take the difference as two source formula, and then thickness. This difference in the thicknesses due to leakage and primary is less than 1 TBL. This 12.87 is lesser than 33. So you have to add 1 centimeter, 1 TBL among which is the maximum. So maximum is 154.8 plus 1 HBT. It comes around 165 centimeter. This way you can calculate. Now, one is shielding calculation for gamma knife. Just I'll give 2-3 slides. So the gamma knife, nothing but you have around 192 to 200 one sources, and there will be 4 concentric circles on the hemisphere, which are really focused at the center of the sphere, where tumor will be aligned. So you can hit doses, radiation from the different direction, and reduce the dose or to the healthy tissue enormously and maintaining the same amount of dose to the tumor. So that fourth figure, you can see that collimator is a diverging collimator which is reaching to the center of the sphere, that is the unit center point, where you can define the field size around 4 mm dia, 8 mm dia, 14 mm dia, and 18 mm. These 4 collimators they have the design, and it has very high mechanical precision around 0.3 mm and I think 0.5 mm radiological accuracy. So really is a very useful. Now, how we are achieving this much? Because in telecom we have 10 to 8 to 10 mm penumbra. Here penumbra is very less. The reason is you have 1 mm around dia of each source. So because 200 sources are 30 curie each and around 5,400 curie total sources. Because geometrical penumbra we have reduced because of reduction in diameter of the source. So accordingly we can reduce the penumbra, and this is a very much required for radiosurgery gamma knife. Next, please. So this is a new model. This is a perfection, and first machine had come, I think, PGI Chandigarh probably, and they have little bit changed the design. It has around 8 independent sectors, and each sector has 24 sources. So 24 into 8 becomes 192 sources distribution. This sector moves basically during treatment. Patient doesn't need to move. So basically they can cover larger field size without moving the patient. This is the advantage of this new model. Now come to the shielding calculation, how to go about this shielding calculation. Something different approach we follow because it's very complex. If you apply our conventional method. So what is being done here? We take the dose mapping. In the factory, what they do is without opening the collimator and with opening the collimator, they do the mapping 1 by 1 or 0.5 by 0.5 by. Means they will make the tube and center of corner of the tube. They will put the dosimeter. So they will map around the whole room with margin, and then they will do the dose rate microsievert per hour in each location, each direction, and in which condition, whether in the transition condition or being collimator on condition. So accordingly, we can calculate. And then how to calculate? I'll tell you. The number of targets per patient is taken around 5 weeks, because whole tumor is to cover, then you have to relocate the tumor by moving the patient through the using a couch table. So around 5 average target per patient is 5, and number of treatment time per target around 6 minutes. So there is a 5 target multiplied by 4 becomes a 30 minutes, and the number of patients treated per day not more than 4, and number of working weeks you can do 5. So just multiply all, you get number of hours beam on time you can see. So 10 hours per week, and during treatment, comes from off position to on position, and then back to the off position of the treatment. So it takes around 1 minute. So 1 minute going, 1 minute coming, become 2 minutes. So just multiply by 5 target per patient, and this one 5 working days. So you will get around 3.3 hours per week. And then the room dimension for gamma knife again 7/6/3, just like a telecobalt room. Okay, next. So look at this dose map. The gamma knife location, and then this is expected dose rate levels emerging from scattered and leakage radiation which exist in the treatment room. So this is in open condition, and this is in a scattered condition, and this is in what we say. This last one is the radiation mapping, radiation map in vertical direction, so that you can calculate the thickness of the shielding. So how to calculate? Once you weekly dose due to total beam on time under without shielding. You can say that 10 hours per week you calculate the beam on time and multiplied by a dose, say 1000 microsievert per hour. So you multiply, you get the because hour get cancelled, only become the microsievert per week. So this will be dose due to shutter on, and then during transition 3.3 hours multiplied by that dose, and then we get a dose without during transition. You add on condition and transition condition total dose. So total dose, once you get the log of RF, this dose divided by what is the permissible dose. So say this becomes 5000 microsievert divided by say it's a public, so becomes 20 microsievert per week. Take log of RF, that becomes the number of TVL, multiply TVL value, provide 22 centimeters, get the thickness. So that with slant thickness, and take the cosine projection, then you get the final thickness of the wall. Next, please. So similar way, just I'll explain shielding calculation for HDR radiotherapy facility. This is the last facility I'm going to touch upon. So HDR, we are using iridium-based, cobalt-based, and all walls and ceiling or primary. Primary barrier is adequate to shield leakage radiation. So scattered radiation is not required to be calculated. Use factor becomes 1 for this. And then workload estimation. You can calculate the workload estimation. What is the activity? What is the number of patient treated per day? Average treatment time per patient, treatment days per week, and exposure at constant. Then you will get beam on time 4 hours per week, and then multiply by this one exposure at constant. At some all, if you multiply, then you get the 20 centigrade per week. So we can calculate. This is a workload at 1 meter. In case of cobalt 60 base, then we are using 2 kV only, but beam on time goes 8 minutes. So accordingly, that workload becomes 60 centigrade per week, and beam on time 6 hours per week. Next, please. So concept is similar. Concept you have to apply. Number of TVL can say that WT by PT square, take log of that, and multiply TVL value, you get the thickness of the wall. Similar calculation for other walls and ceiling. Next one, please. So this is the way we can calculate the thickness of all walls and the ceiling, even on floor also, in case of basement. And then what will be the door? Doors at entrance door. Doors at entrance door will be radiation doors at entrance door due to wall scatter and transmitted dose through maze. So each component you can calculate, like weekly radiation level due to scattered radiation at entrance door is nothing but alpha E WET by dW dt square. It is scattering, basically scattering from the wall surfaces. Next, please. So this is the radiation you have received. Now 40 MR per week scattered radiation minus permissible dose for what is that calculation from maze thickness. You can say 40 minus this is scattered radiation minus, and then you can calculate the thickness. This will be slant thickness multiplied by TVL value. Cos theta. Then you get the final thickness of the wall of maze. Okay. So just we'll do 2-3 examples on radiation survey and assessment of weekly radiation level. Now most of the physicists do the mistake here. Once the radiation level is more than 1 MR per hour, they say that radiation level is very high. It cannot be. They start doing shielding additional. So this is more practical things. I'll explain you. So for doing a survey, what we need, that appropriate survey meter we need for like isotope based, GM based, and chamber based, both survey meters. Okay, if I have ion accelerator based, then you should have ion chamber based survey meter. And then if energy is more than 10 MV, then it should use neutron survey meter as well. And then we auto phantom for scattering condition. So most important is TADR, time. Next, this weekly TADR time average dose rate. So now we use weekly radiation. In US NRC, they hourly is also limited there. They do, but we have only this requirement: weekly radiation level at any location. So this is given by WET into IDR, nothing but survey meter reading divided by at what dose rate this survey is conducted. So more the dose rate you use during survey, more the what will the survey meter reading will be there for the same thickness. So unless until it evaluates using this, you can't say it is safe or unsafe. So maximum expected from this equation, you can rearrange IDR equal to weekly radiation level into the dose rate. Dose rate multiplied by dose rate, because my what we say for linear etc. monitoring unit per minute multiplied 60 per hour divided by WET. So using this, you put the value. Say is a public area, 20 microsievert per week is a allowed value, multiplied by 600 monitoring per minute. Suppose you have taken dose rate during survey, multiplied 60 divided by workload 10.6 5 centigrade per week, and use factor 1/4 you will get around 28.8 microsievert per hour. So even for primary in the public location, you can, if radiation level is less than 28.8 microsievert per hour or 2.88 mR per hour, then it is safe. You cannot say unsafe. And in case of radiation worker, change this 20 to 400 microsievert, and it comes around 576 microsievert per hour. So in MR, you could say 57.6 MR per hour. This is also safe. So for this was for linear, and now for SDR, similar we can calculate. It is around coming, because workload is 20 centigrade for iridium base, then then it comes around 5 microsievert per hour for public area, and for worker it comes around 100 microsievert per hour. That means if radiation level is 100 microsievert per hour or 10 mR per hour for worker position, then is even that is safe. It means beam on time was 4 hours per week, then multiply by 10 hours, 10 mR per hour, then becomes 40. So 40 mR per week is acceptable limit. So that's what I have derived it. Next, please. So just one practical table I have created. So what you have to do is you have to take radiation survey with phantom, without phantom, at all coordinate angle. You record the radiation for photon, for neutron, and mark out the location. So calculate the TADR, and dose rate is very important. At what dosage you have carried out. Suppose 600, you are getting X MR per hour, and if you are reducing the dose rate during survey 300, so survey meter reading will come by factor of 2. So it is very important to note. So to calculate TADR, you just use WT into IDR divided by dose rate. Use this one and then calculate. From this table, you can work out for photon it's coming 13.8 microsievert, and neutron almost 0. No reading is there. And then sum it all TADR, you'll get 13.8 microsievert per week, which is less than 20 microsievert per member server. That is safe. Next. So for secondary barrier, ideal is a theoretical, but practically we are not doing that way. Theoretically, you can do that weekly radiation, nothing but there will be leakage workload, there will be patient scatter. So IDR due to you can calculate from the survey meter that instantaneous dosage due to leakage, how much it is coming, what is the workload divided by dosage, and plus IDR in patient scatter condition. Means there should not come head leakage, only patient scatter condition, and then workload of primary multiplied by use factor, there will be 1, and a summation of all this should be less than permissible dosage. So how do you calculate that instantaneous dosage for patient scatter? You just reduce total radiation, because once you put the phantom, you get radiation beyond the secondary barrier due to head leakage plus patient scatter. So minus in one condition, just close the collimator, you'll get the radiation due to leakage radiation. So second, the radiation due to leakage, you reduce from the total, you get the IDR from the for the patient scatter, and using this equation calculate. Now, okay, next. Okay, just one this example I'll give you, then get more clarity. Suppose radiation level observed in an area beyond the wall of iridium 192 based SDR brachytherapy facility, which is found to be 40 microsievert per hour with present activity of 5 kV. Suppose 5 kV source is there, and after wall you doing radiation survey, got 40 microsievert per hour, means 4 MR per hour, and find out whether this radiation level is within the acceptable limit, which is occupied by account staff. If radiation level is not acceptable, then what would be the additional shielding in terms of TBL is required. So weekly radiation level can calculate. Workload is 20 centigrade per week, multiplied by survey meter reading is a 40 microsievert per hour, and use factor 1, occupancy factor 1, and divided by what is the dose rate? Dose rate at 1 minute, nothing but gamma A by D square. Gamma is 0.5, R 0.5 centigrade per hour, and multiplied by this one, 4 QD. Sorry, 5 QD. 5 QD is there. So just to multiply, you get around 64 microsievert per week. Means this is greater than 20 microsievert if public. Then what will be additional thickness? Take the log of 64 divided by permissible dose limit is 20 microsievert. Then you get number of TBL. So number of TBL, if you want thickness multiply with TBL value of concrete, then you get around 7.58 centimeters of concrete thickness additional required to this level, whatever required for the members of public. Next, please. Okay. Just one last is there. Suppose in case of simulator, physical simulator you have, how to calculate weekly radiation level. Then you have suppose during survey you got 100 microsievert per hour, and machine was operated at 40 MA and 120 kV under full scatter condition. And here in case of physical simulator, you can use just conventional simulator 500 MA minute per week. So TADR is given for simulator or city simulator or actually equipment is weekly workload in MA minute per week multiplied by survey meter reading divided by applied MA. So you put it this value, it's coming around 20.83 microsievert per week, which is less than 400 microsievert. So this is a safer. So there is a two type of workload. One is tube workload, and this is a facility workload, MA minute per week. So next, I think it's over. Thank you. Thanks for attention. I think I have exceeded the time. Dr. Bhatt?
Yes, sir. Yes, I was well within time. So
Yeah.
this is an interesting topic. So I will request to Dr. Satish, please coordinate for all the question answer and queries on the chat box. Dr. Satish?
Yeah, I'm there.
Okay, please.
Yeah. Sir, thanks for this wonderful lecture. So there are a few questions from the participants. Can I ask one by one, sir?
Yes.
Hello, sir. Can you hear me?
Yeah, please tell me. Please,
Yeah.
can
The first
you
question is, yeah, they ask about the workload calculation for radio iodine isolation room.
Okay. Radio isolation. So in radio iodine isolation ward, what we say that around maximum activity is 300 millicurie of radio iodine is being used for therapy. Okay. So how many patients? That depends. They have to declare in the planning stage itself. So if one bed, then 300 millicurie you have to take per week, and accordingly you can calculate that what is the multiply by exposure rate constant, and then you get the radiation without shielding, and then what is the design code. Again, principle is same. Reduction factor is a dose without shielding divided by with shielding. You can calculate and multiply by number of TVL value, then you get the thickness, and more the watt, more the, then you have to calculate accordingly. Yes.
So next question is that, should we take patient transmission factor for the shielding calculations of iodine 131 isolation room?
normally we don't take. We only take that it is as the 300 millicurie without patient. So that is worst case scenario. But
Okay,
yes,
sir.
one can stimulate that will be also within the limit. There won't be problem. But as a policy, it is assumed that there is no patient. Like 300 millicurie you are taking, and conservatively it will be safer.
Okay, the next question is that does NCRP 151 report considers PDD at 10 centimeter for the workload calculation?
No, they don't talk about. They talk about what is the dose you are giving. So they write directly like 400 centigrade per patient. So what we do, we say that 2 gray per patient. Then you are using PTT. We say that this are the divide like for telecobalt. You are dividing a PTT of 50%, then becomes a 400 centigrade. So concept is same. They don't use PTT, but they use already they have used PTT value in their mind, and they have used around whatever the dose is coming at the max. That dose they have taken per patient.
The next question is that do HVT and TVT values consider broad beam geometry?
Correct. So it's a very good question because HVT, TVT determine in good beam geometry, narrow beam geometry. So narrow beam geometry does not simulate the scattered radiation. So whereas in our practical purpose, all the beams are broad beam. So scattered component will be increasing the value of I. I means intensity, transmitted intensity in broad beam condition. So accordingly, your mu value will come down. So mu value come down, TVL will be high. So we use.
Okay. The next question is that. Hello?
So we lost you.
Hello.
Just wait. I think there's some internet issue.
Okay.
Hello. Hello.
Yes,
So we just lost you. Can you switch off your video to get a good bandwidth? Oh, sorry. I think again sir is not here. So give me 1 minute, please. Okay. Can you unmute, sir, please?
Just
Okay.
is it audible now?
Yes, sir. It's audible.
Yeah, please.
Yes. Dr. Satish,
The next question is why design goal P, capital P, are stated in terms of equivalent dose instead of effective dose. As we take P equal to 20 millisievert per year for radiation worker, then why is this anomaly? And followed by one more question is that what is P in shielding calculation? Is it permissible dose limit or permissible dose equivalent?
Okay, I'll explain it. See, when equivalent dose you're talking about, these are basically you're talking about organ dose. When you are in your broad-based condition, your whole body is getting exposed. So there is no difference between equivalent dose and effective dose because if WT becomes 1, because whole organ is being expose. So that's what a dose equivalent and effective dose are both same under this condition. So there is no difference in
Okay,
the
next.
hello.
Yeah, sir. Can I go to the next question, sir?
Yeah, please.
How does the shielding for Halcyon and tomotherapy varies from that of LINAC?
From
From that of LINAC, linear
okay.
accelerator.
Look at as I told that trivial value depend on what is the material and what is the energy of photon. So physics wise, all are using 6 MB. Then my design goal is same, say public 2 MR per V. Thickness should be same, ideally. It should not, because it is not the same. The reason is you have a different methodology of dose delivery. For example, in cyberknife, you are delivering the dose from 100 to 250 direction. So your use factor becomes much less compared to conventional accelerator, where they are taking 0.25 1/4, and here only 0.05. This basically use factor is going to multiply by workload, then you get that amount of dose. The dose has reduced, so thickness will reduce. So, but the beam on time is high, so that the thickness is go up. So in this way, thickness are varying for the same area, same material, same design goal. Similar way, Halcyon also, because you are teaching slice by slice, and that beam on time or maintained goes up around 5,000 to 6,000 per fraction of delivering 2 grade dose because of its technology. So here also scattering radius is very high, and primary was very high, but it has come down because of providing beam stopper. So this is the answer.
If dose rate at door is given for neutrons and photons in microsievert per hour, how to calculate TADR?
If the dose rate at
Door is given for neutrons and photons in microsievert per hour, how to calculate TADR?
Okay, so TADR for photon, you are going to calculate WUT by PD square. Sorry, dose rate. So dose rate at photon. So here, dose rate you have to take the same, whatever you are taking at 1 meter, and only the thing use factor you have to take 1. In this case, at the dot, no difference. Then you have to sum it of both neutron plus photon dose, and it should be much less than 400 microsievert per week at entrance door.
Okay. Why use factor is always 1 for floor calculation?
Because most of the, if you look at the clinical establishment, dosimetry, QA, all the things, we are taking 0 degree gantry angles. Other gantry angles very less. So for the safer side, it still can be optimized, but for safer side, you take 1 because. And however, if suppose there is a parking in the basement, you can take use factor 1/4 because your what you say guard may not be available all the time, or maybe some storage room people may not be always there. So accordingly, you have to choose use factor, occupancy factor, but use factor you have to take 1 because of this reason.
Okay. If a bunker of dual linear accelerator has an electron and a variant linear accelerators, will the workload be same or different for the 2 machines?
I mean, you are talking about conventional Linux, but for conventional Linux, no?
Yes, sir. 2 different companies.
Correct. Because company both are making, no? Like Halcyon, that company is making conventional accelerator, so we cannot compare. So yes, you have to compare your like 2 women versus LG, that we have compared. So there is no difference. Both will be same because throughput is almost same.
Okay. Next question is, suppose a department using 6 MB LINAC So if they want to replace it with tomotherapy with the same shielding, will it be possible?
There would be some little modification, but that can be done. Because for tomotherapy, it comes around, I think, 130 centimeter. But here, higher at the beam or the primary beam. But secondary barrier, little bit, that is also comparable, and the mesh will be higher. So with minor modification can be installed. There won't be problem. 6MD. Even Halcyon and tomotherapy both can be installed.
Type Linux.
So IMRT factor for C-type Linux.
C-type Linux. C-type Linux.
C-type Linux, no? Means you are talking about tomotherapy.
Yes.
None? Hello?
Hello, sir. Yes, sir.
This you are talking about Halcyon or tomotherapy, no?
They asked a question about a C-type Linux. MIT factor for C-type Linux.
C-type Linux means, what do you understand this rotating anti-type, no?
Yes, sir. I think so, sir. Because question from a participant, C-type Linux.
No, that again varies, no? Like C-type, if you talk about tomotherapy, it can go about 16. Whereas
C-type Linux means I mentioned about like Varian and Electra type Linux. That's what I just mentioned.
Correct. And for no, Halcyon, it may be around 2 to 4 varies. That depend on like VMAT. If VMAT use IMRT factor is very less, not very high.
Okay, so next question is that during radiation survey, should we consider IDR only or TADR needs to be considered also?
No. IDR will be required, but TADR has to be evaluated. There is no money. For example, in brachytherapy, even 10 MR per hour at control console is also okay. But unless until you evaluate by TADR, you cannot say that it is safe or unsafe. So that is must in all facilities.
Okay. When we calculate width of primary barrier, we take SAD plus D plus D1 by SAD. How to get D1?
So if some question, someone asks you that this is the distance and we'll calculate the thickness of the barrier and width. So that in that case, D1 will be not applicable because you do not know. So unless until you calculate the secondary barrier thickness just adjacent to primary, D1 will not be able to achieve it. So for this reason, you need to calculate first primary barrier thickness, then width roughly, then adjacent to that, once the barrier primary barrier ends, there you calculate secondary barrier thickness, then primary minus the secondary barrier thickness you calculate, that becomes the D1. So then you can calculate D1 protrusion. You'll get the protrusion.
Okay, so next question is that how to calculate neutron dose behind the primary wall?
Okay, neutron dose, because you have you can calculate the flux, all the three components. Then you can calculate the dose, flux to dose conversion. So behind the barrier, you can calculate what is the transmitted dose. Suppose due to photon, you are getting 220 centimeter concrete, and a TVL value for this neutron dose from head, whatever is coming, it is 22 centimeter is the ordinary concrete. So 220 divided by 22, 22, so it becomes around 10 TVL. So your reduction of neutron dose will be 10 raised power minus 10, so almost negligible. So there will be problem.
From shielding point of view, do we have to consider neutron dose from energies greater than 10 MeV electron, similar to 10 MeV photon.
No, electron doesn't have that much energy interaction. Proton interaction is not that much as photon. So we don't need to consider. If yes, only electron is there and no photon, then you have to consider. Otherwise, whatever shielding is calculated for photon, it will take care of the neutron. Neutron generated from electron beams. At all.
Okay. When should we use the same dose, like 20 millisievert, 1 millisievert limit for design purpose, or should we use still lower for higher safety?
See, ideally in other countries they have given dose constraint. For example, US, so they don't take 20 millisievert for occupational work. They take 5 millisievert. So they have reduced to factor of 4, no? So by factor of 4 they have reduced the limit. That is called dose constraint. But in our case, we have evaluated, as one slide I showed, that there is a lot of assumption. As assumption is, there is a patient during treatment always, or phantom during dosimetry. So there will be attenuation in primary beam, but we don't consider patient or phantom with there, calculate. So this is the overestimation. So this is again conservatively high thickness we are giving. Number 2, there is a thickness head leakage. Head leakage if we take 0.1%, but always they give higher thicknesses around the target, then again reduces the dose. And there is a direct, when there is a radiation, central axis beam falling on the primary beam, that is perpendicular, and that we are considering a distance, and thickness will be straight. And when you are going other than central beam axis, the other direction, any direction, then there will be oblique thickness, slant thickness. So distance will be higher, as well as thickness, slant thickness will be increasing, but from the same thickness of the wall. So it's again reducing the radiation level. So these are all conservative factor. So need not to take other factor. So this will take care.
Okay, so the next question is
So,
why we.
one more point I want to add, because we measure the radiation level always less than I think 3 millisievert is coming for radiation worker. So nothing to worry about. Yeah, please next.
Why we don't consider PDD in workload calculation of chemotherapy or cyberknife? Why only 6 MV LINAC or dual energy LINAC?
No, we are considering their dose rate. What is the dose rate is there, and what is the beam on time, right? So dose rate PDT we are considering because what is the total dose? For example, tumor is located at 10 centimeter depth in the tumor, and we want to deliver 200 centigrade. So your tumor dose, dose rate at Dmax would be divided by PDT. That if there is a dose of 400 centigrade at Dmax, then only you will be able to deliver 200 centigrade tumor. That means, so PDT you have divided, then you have got this value. Whereas in tomotherapy, we have already taken care that what is the actually beam on time, 7 minutes per patient, and multiply dose rate and all factors. So already taken care. So PDT is not required in this case.
Okay. The next question is that why the bulge out of for LINAC is rectangular, but for a telecobalt is slanting? Asking related to that primary beam.
Yeah. So why it is because of when we allow electron to hit a target material, so you make the what we say dose rate map. So along the axis direction of electron beam, look at maximum radiation, and thereafter reduction and drastic reduction in the intensity with respect to angular distribution. And where is it telecobalt, you have a significant amount of dose intensity, even at a larger angle also. So that's what there is a slant type of thickness, and here we don't require that kind of design. However, If we want to more optimize, there is also based on the angular distribution we can calculate. But the room will be looking very odd. That can be done. Yes.
The next question is, should we consider biological decay for shielding calculations of radioiodine isolation room?
Yes, basically, because half-life 8.4 days, isn't it? So there we don't consider. Whereas in case of PET, half-life is very, very small, like F18. So there we consider. Physical half-life, because biological half-life doesn't mean physical half-life is so less. So as per effective half-life equation, if either of half-life, either biological or physical half-life is very small compared to other. So smallest one will be taken into consideration. Yes.
Okay, so the next question is that, is there any guidelines of shielding calculations?
Hello.
Hello. Yeah.
Yeah.
Is there any guidelines of shielding calculations for high energy, say 30 MeV, Linac for radioisotope production?
Yes, we have. You can use NCRP 144. You can have many IA document is there. You can use.
And the next question on the radio diagnosis. When different examinations carried out in diagnostic X-ray facilities with a different KVP and MAS are used for each examination, should we consider max KVP and maximum MAS or MAS corresponding to max KVP only?
Actually, RD is to be maximum K, but what is the practically? That maximum KV is always not used. So, what is the basically we integrate that what is the MAS, what is the number of procedure, what is the MAS in each procedure, multiply it and get that, like head and neck. So you're doing chest X-ray. Then what is MAS? How many patients? You get the MAS. And whatever the KB is there, it may not be required 120. Suppose machine is having a capability of 120 kVp, but most of the chest X-ray may not be using that one, maybe using 60, 70. So at 60, 70, whatever MS is there, just so take this one. For a skull, higher kV are used. So you have the data for that kV, what is MS being used for each patient. You add all MS divided by 60 given coming to MA minute. And similarly, all type of cases, then your MA minute per week per type of cases. So sum it all MA minute per week. So that is the workload of X-ray facility. So like beats any facility. MA minute per week.
Follow one more question is that, should we add workload for all the examination as mentioned above, or different KVP examinations of different exposure rates corresponding to them? Which factor should be used for converting milliampere minute per week to dose rate per week when different KVP are used?
I couldn't understand this question.
So the question, should we add workload for all the examinations on different KVP examinations have different exposure rates corresponding to them? Which factor should be used for converting milliampere minute per week to dose rate per week when different KVP are used?
Normally we take that 100 kVp. So around 10 mR per mm minute corresponding to 100 kVp. So that conversion factor on the use.
Okay. The next question is that, out of head leakage and scatter radiation, which is more predominant in Linac and telecobalt?
In telecobalt is head leakage, and Linac is also head leakage only predominant. But they are very close. Sometime depend on, I think cobalt little bit patient scatter is higher.
The next question is, does the size of maze has any effects on the intensity of radiation outside the door?
Does the
size of maze. Size of maze wall has any effects on the intensity of radiation outside the door?
Then there is two things. One is the maze wall thickness, and sorry, one is the maze area. What is the maze? What is the width of maze area, and what is the thickness of maze? So basically, if you, maze area width increasing, basically now be like cobalt, you have 1.8 meter. For example, linear accelerator, you have 2 meter. If you put from 2 meter in linear, you are making 2.5 meter. So there will be huge amount of scattered radiation. So that is not acceptable. Then you have to provide shielded door. So that it should be optimized. So 2 meter to up to 2.2 meters is okay. Otherwise, you have to have either longer maze width length, or you have to provide some shielding at the door.
Okay, so the next question is that can we use 15 MV bunker for 6 MV linac? What are the things to be considered for changing energy of machine?
Can we use a 15 bunker for 15 MV for installing what?
They asked us, can we use 15 MV bunker for 6 MV linac?
Okay, that's very
calculating for 15 MV, can we use it for 6 MV linac? What are the things to consider for changing energy of machine?
why are changing the energy? Already you have decided.
Okay.
I have 15 MB bunkers. I want to 6 MB. So energy is already decided. No, then I got 6 MB. No, there is no shielding requirement. Only that legal requirement. You have to take approval for installing 6 MB. Otherwise, technically there is no problem. If 6 MB is there, then you have to modify for meeting a shielding requirement of 15 MB.
Okay, so the next question is the difference between shielding requirements for 6 ME flat double F and 6 triple F beams.
Okay. Because nowadays coming in the mixer, so it is very difficult because 4 or 5 beams are there. So if flat beam is there and you have calculated, this will take care of the unflat beam, because unflat beam is having low TBL value. We have measured around, it is coming out 29 centimeter, something like that. Whereas the 6 ME flat beam is coming with 34 centimeter. So if calculator flat, it will taking care of unflat beam also. So no need to worry about it.
What type of neutrons are mainly generated in the linac head when photon energy is greater than 10 MV?
These are just like a neutron generated from nuclear reactor. They are fast neutron, and after interaction they get thermalized also. So all type of radiation from thermal to fast. But coming at the door, the radiation, energy reduces to kV order. Yes.
Okay, so next question is that why we do not scale the dose limits below 1 week for the barrier design?
See, you can use even annual dose limit, but the thing is, we want to break down. So this gives more average, better average, averaging. If you go to per hours, then even it will be better than weekly. But weekly is also good enough for taking calculation purpose, because it's a worldwide also acceptable.
Then, sir, why do we take distance from isocenter for head leakage barrier?
See, we want distance from the point source to point of interest, because here in head leakage, what is that? This your position of source keep on changing from say 360 degree in the vertical plane is rotating. So if it is helical, so every angle you have to see, then you have to find out. So it is very difficult. So rather than we take this source location at isocenter. So this is giving, if you arrive shielding requirement, so this will be what we say conservatively safe, because there is distance from the source to point of interest will be again reduced, and that slant thickness will be again here nodes land thickness, there will be direct radiation. Then thickness you have to provide more. If you take location of source at isocenter, so conservatively safer again. So that's what we take at isocenter.
Okay, so next question is that using 4 hours per week and workload 20 centigrade per week and same room dimensions, we got 48 centimeter in concrete. This 45 centimeter in concrete is not sufficient, but in this layout 45 centimeters given. Please clarify them.
Very good question. Those were asked because earlier TVL value was 13.5 centimeter of concrete. Now it has been reduced to revised to 15. I think 1 or 2 centimeter concrete. So because of this, she is getting more, or he is getting more thickness. So can be modified, but that, as I said, a lot of conservative approach is there, so radiation level is not higher while calculating TADR. So we are not revising. Certainly, it will be revised in future.
Okay, sir. REM counter is absolutely appropriate for neutron survey. And one more question is that any other survey meter is used in India for neutron survey?
Okay, so normally there are 2 types of neutron survey meter. One is helium-3 based detector, another is BF3 based detector, basically survey meter. So BF3 based detector is being used where the dose rates will get high because it has advantage. Because of QL is very high, then because as I told earlier, that when the neutron is there is an interaction and it produces the gamma. So gamma has to be rejected from your detection system, and because of higher Q value, this gamma doses can be rejected in case of BF3 very effectively. Whereas helium-3 Q value is very less. I think 0.7 MeV, and here 2.3 MeV. So the gamma pulses are very weak in case of helium-3, and so then there is a rejection of gamma is very difficult in helium-3. But at the same time, it's what we say cross-section, nuclear cross-section of interaction of neutron in helium with helium-3 is around 5,004 Bohr, and whereas in BF3 nuclear cross-section is audible?
Yes, sir. Yes, sir, audible, sir.
Whereas in case of BF3, so B10, basically B10 is the isotope, B11 is the normal isotope. So neutron react with the B11, and this cross section or probability of nuclear reaction is around 3,800. So it is lesser than 5,400 compared to helium-3. So helium-3 is much sensitive. So where the radiation level is very less, the sensitive detector is required, then helium-3 is to be used. So as long as you are able to detect beyond the minimum detectable limit and predictable reading, both detector can be used. And number 1, these are normally from linear accelerator we are talking about, right? Where energy is not very high. When you go for proton accelerator, where energy is very high of neutron, it guys go up to 200, more than 200 million ton volt of neutron energy. So there, hello.
Yes, sir. Yes, sir. Audible, sir.
Yeah. So there, this kind of detector will not work. There is another detector have been developed like Wendy-3. So that has energy range from a thermal to 2.5 GeV. So that is being used. That Wendy-2, that's a model name, and that being used by proton therapy facility like Tata Memorial Hospital and Apollo Hospital. Yes, please. Yes, please.
Yes, sir. The next question is that
Yeah.
yes, sir. In brachytherapy, idea doses given, how can I calculate whether it's safe or not?
IDR is, I told you, that TADR equal to IDR into workload divided by dose rate with that activity at 1 meter. For example, 5 curie. So 5 curie, what is the dose rate? 5 into 0.5 Roentgen per hour per curie at 1 meter, exposure rate constant. Then you get the 2.5 Roentgen per hour. And numerator you have 20 centigrade. And again, numerator you have IDR, say 10 microsievert per hour. So you'll get the radiation level microsievert per week. Then you can compare with permission dose limit, whether for worker or members of the building. Yes.
The next question is, what is TVT value of concrete for iridium 192?
Is a 15.2 as per revised data for IS safety series number 47 and NCRP 51. 151.
What is the use factor for halcyon? Is the same procedure as thermotherapy?
Type C, but I understand only that rotating type, isn't it? So this is like halcyon. It is a point one you can take in the worst case scenario. So in case of halcyon, also in case of thermotherapy, it's also 0.09, you can approximate 0.1. In case of Siddharth 2, is new machine coming, also you can take 0.1, something like that. These are RC type.
The next question is that what is the thickness of wall required for iodine 131 therapy room?
Around 23, less than 23 centimeter of concrete.
Okay. How do we account for the earth bit for the shielding calculation?
How do we?
How do we account for the earth bit for the shielding calculation?
It's 8 beds, no?
Yes, earth bit.
Okay. So 8 beds are then again you have to calculate the take the activity, same principle. Activity, what is the number of activity per patient, then what is the number of patient, and then multiply, then get the dose without shield, and divided by design goal, get the reduction factor, and multiply by number of TVL, and get the thickness. But you have to consider for all dosage due to all 8 beds.
If we have 6, 10, and 15 MV, and we use 6 MV for IMRT and VMED, then how to calculate workload?
But we do not know. You have taken 6 and 15, and though clinically you are using 6 MV, but the thing is, in 15 MV you are using, then there is going to exceed the dose. Number one. Number two, suppose you don't want to use 15 MB and you are going to use 6 MB. And then whatever the monitor unit is required for IMRT, multiply by use factor. And whatever the number of patients you are treating per day, in conventional, you have much higher compared to IMRT. So almost product of use factor workload remains similar. So it is not affecting shielding. In contrary to Western countries, reason is there, they take only 30 patients. We take 70 patients. So in their country, IMRT factor really matters. But our country doesn't matter much because of number of patients take very high. So accordingly, monitor unit is very high income, even in conventional treatment also. So we take IMRT, then patient through to come down from 70 to maybe 25. So accordingly, monitor unit come down. Total.
During calculation, okay.
Please.
During calculation of PADR, a survey meter reading convert to for max activity as during survey activity is less than the max loaded activity.
So I told that TADR calculation from this the two methodology. One is as I told that TADR is equal to workload into IDR divided by whatever present dose rate at 1 meter, you have calculated the present activity. You use that one. So R, you have a beam on time 4 hours per week with 10 curie. Then it was 10 curie. Suppose activity is 5 curie. Then dose. Then your beam on time is go up maybe 8 hours, isn't it? By factor of 2. And then you have IDR has come down by factor of 2. So this ratio gets cancelled. IDR has come down, and that beam on time has gone up accordingly. So this will be cancelling out each other. So this way, how we are calculating TADR equal to activity at the time of the beginning 10 curie divided by 5 curie, whatever present activity of 4 curie, 3 curie, whatever, into IDAR. That's all. And beam on time per week, 4 hours per week. So you'll get the same as using dose rate concept.
Okay, the next question is how to calculate TADR at different gantry angles 0, 90, 180, 270 degree IDR values.
Primary or secondary?
They are not mentioned this. They said how to calculate TADR at different gantry angles 0, 90 degree, 180 degree, and 270 degree IDR values.
They can calculate in all gantry angle by taking use factor, and then they can sum it up for all 4 components, and then they compare with the design goal.
What is the difference between controlled area, uncontrolled area, and supervised area?
Controlled area means your control console and treatment. Uncontrolled area, like you have what we say, like you have reception, you have account room, you have many things around the bunker. So this is called uncontrolled. You don't have any control. So there is some area where you can supervise, have a supervisor, like in nuclear medicine. So though you have not introduced concept supervised area, but these are the supervised area where limited access is there under supervision of RSO. That is called supervised area.
The next question is that can you explain proton therapy shielding related to that?
Proton therapy shielding is very, very complex. As I told that this analytical calculation does not hold good alone. With proton therapy shielding, there's a Monte Carlo generated data source term, you call source term per MA minute per energy and per beam current. So what is the neutron dose and photon dose? Then these are generated from Monte Carlo data. Then you can use analytical calculation. Or the whole system you can do the modeling and calculate the dose rate beyond the shielding. So in that way, basically whole system they are doing with the Monte Carlo, and similar way we had a committee set up and they have evaluated. So based on that, it has been approved.
The next question is that X1 and X2 are TADR for 6 MV and 15 MV respectively for secondary barrier. How will you account for their contribution for thickness calculation? When should be iteration do for thickness calculation, and how many iteration taken account?
Then 2 photon, what is the question?
X1 and X2 are TADR for 6 MV and 15 MV respectively for
X1,
secondary
X2,
barrier.
X1, X2, 2 photon beam you're talking about?
Yes, sir.
X1, X2, 2 photon beam you're talking about?
Yes, sir. Yes, sir. That is the question.
This
X1
X1,
and
X2,
X2 are
Yes, sir. X1 is for 6 MB and X2 is for 15 MB.
Yes. So then that is very simple. Your respective workload you take, no? For calculation of TADR. Respective TADR, IDR and respective workload can be calculated. Yes, next question, please.
Yes, sir. Next. What we average the position of gantry for calculating leakage and take it at isocenter, but in calculating RF, we take use factor of 0.25 as mentioned in TG47. Why so?
TG?
We average the position of gantry for calculating leakage and take it at isocenter, but in calculating RF, we take use factor of 0.25 as mentioned in TG47. Why so?
See, because the cardinal angle in a leakage always there is a radiation whenever beam is on. So use factor, you have to take 1. What is use factor? Use factor nothing but what is the fraction of beam on time during that particular wall is facing radiation. So in case of leakage, always facing them become 1. In primary, only facing 1 with the gantry angle is directing such way that is receiving the primary. So at the convention, we are taking 4 cardinal angle. So 1/4 that becomes the 0.25. Whereas in and Halcyon, we have 0.09 or maximum, you can say, was 0.1. So that's what, depending on the what type of technology you are using, according to use factor is to be decided based on the machine.
The last final question is that, sir, iodine 131 isolation room, P is in MR per week, but exposure rate is MR per hour. Should we take it as MR per week directly because only one patient will stay for that week? Even though the biological decay also reduces the exposure rate at the end of the week.
Always when radiation protection comes, always conservative, should be conservative, let it be higher thickness. So there will be reduction, of course, but if you calculate using decay correction, using the half-life of 8.4 days, certainly it will come down, but this will be safer. Yes, ideally that can be applied even by decay correction if you want more optimal thickness. So thickness will not much reduce even using by this correction factor. But ideally, practically, I mean, theoretically, yes, it can be used.
Okay, sir. Thank you. Thanks for this wonderful presentation, sir. And thanks for this questions. I've given a clear explanation answers for this, sir. Now I'll give it to Secretary Dr. C.P. Bhatt.
Thank you all participants. Thank you, Sahni sir, for explaining in detail about all the different type of modality available. You covered LINAC as well as TOMO as well as Brachy as well as all type of, and particularly thank you for taking all the questions. You know, there are many questions from participants. And although we are expecting it for 1.5 hours, but you know, it's I think near to 3 hours. so as this is a very interesting topic and topic of interest of all the faces, and many faces have many queries. So you know, thank you for taking all the queries, and hope you know this talk will help to you know exam going candidate, particularly for RSO exam, and you know working faces also for doing that day-to-day calculation of shielding calculations. So thank you everyone, and with this, you know, it's the festival season, festival time, so I will congratulate to all, you know, best wishes for you know upcoming festival Diwali and next festival week. So with this, thanks to all, thanks to sir, thanks to Satish, Dr. Satish for moderating this session. And in starting, you know, there were some glitches, technical glitches, but sorry for that. Sorry for inconvenience, but you know, at end it was a good good you know interactive session. So with this, thanks to all, and thank you, sir.
Thank you, Dr. Sir. Thank you all.
Thank you so much.